Okay, good morning, everyone. I'm very delighted to welcome all of you to our workshop. So at the beginning, let me give a short introduction of our center. So our center name RIKEN Center for Advanced Intelligence Project. And our center established in 2016 under the support of Max. Currently, we have 137 employed researchers, and 42% are international researchers, and 23 are female. Also, we have many visiting scientists and students from domestic and the intern from overseas. So this is our office and the open space where we are now. And also AIP actually distributed in whole Japan. And original is a 10 years project. And this year is the last year. And fortunately, our center has been already decided to extend it to 7 years more till 2032. And our center has 3 groups. One is generic technology group. There are many different teams. And the AIP director is Professor Masashi Sugiyama. He's also full professor in University of Tokyo. And second group about goal-oriented technology. And they have many research for AI for science and AI for social problems. Also, we have third group is AI in society, which about many social issues and ethics research. And in generic technology group, we develop new theory about deep learning and also new method for machine learning. And in application goal-oriented group, we develop many AI for science, especially for cancer detection, ARS, early diagnosis, or some medical science and material science. And in social problem, we have worked like Fukaku-based earthquake simulation and remote sensing, and also earlier healthcare and something else. And this is AI ethic guideline. It's worked by the third group. So include AI security and reliability. Here is the statistics about our previous publications, especially in last year, we have 41 NeurIPS paper and 37 SML and 19 iClear. Also, some team leaders are general or program chair for iClear last year and AI Stats, MTS Khan, and also Masashi Sugiyama was general chair for IEEE AI conference. They also give plenary talk and a keynote talk in many conference. And we have very broad collaboration partners with the North American, Europe, and Asia, many universities in China. Also, we had held a lot of workshops in past 10 years with many universities, especially I organized a workshop with Shanghai Jiao Tong University 2 times, one in Shanghai, one in Tokyo. Okay, now it's a final year of AIP Center. So each team is holding a progress report meeting to share their research achievements to society. And here is a list of workshops in AIP Center. And today is our workshop in the end Tensor Learning team. Each team will continue to hold events sequentially until the end of the year. And the AIP Symposium will plan at the end of fiscal year to summarize the center's achievements. Okay, so this is the next AIP plan. So in next stage, AIP will reorganized, and some new team will be established. We divided into 3 domains, and again, 3 groups: domain intelligence, and the physical intelligence, and the mathematical intelligence. Now, I think it's time to start the workshop.
Okay, very good morning to everyone, and it's a great pleasure to be here, and also to see so many familiar faces, some of them I haven't seen for ages. Today I'll be talking about interpretable AI. And so what is it we need to do to actually deploy AI in pressing societal challenges? And absolutely, tensors are one of those things, one of those tools that have invaluable role in that. So I come from Imperial College, which has a long tradition of machine intelligence. And often I say machine intelligence rather than artificial intelligence, because machine intelligence kind of implies that what you produce actually works in practice. So machine intelligence at Imperial started with Professor Denis Gabor, and basically everybody in this room knows about him. He got Nobel Prize for holography, of all things, but you've all played with Gabor filters and such like. So he was basically superseded by Professor Colin Cherry, and the team at RIKEN has long tradition in blind source separation. So Colin Cherry introduced the cocktail party effect, and then he was a mentor to Professor Tony Konstantinidis, who is a pioneer of our digital presence. Now, when I talk about our digital presence, where are we now? Fast forward many, many years, we have huge models with trillions of parameters. We can compute many things, but we have also pressing issues. For example, the MIT Technology Review here, they said that making an image with a generative AI uses as much energy as charging your phone. So, well, we all like to play with various models, but think a little bit about how much it costs our environment. Here you can see, for example, from the same article by MIT Technology Review, that, now this is from Google actually, generating 1,000 images with a powerful AI model is responsible for roughly as much carbon dioxide as driving the equivalent of 4.1 miles in a car. So it's about 6 kilometers. So if you're preparing for a conference and you want to generate many, many nice images, you easily generate several hundred, 1,000 images. And that's considered clean. Driving a car for 6 kilometers is considered dirty, because you can maybe take a metro or you can walk even and such like. So there's many, many, many aspects we really need to look into. So Google estimated that an average online search uses 0.3 watt hours of electricity. So it's equivalent to driving 0.003 miles. But I've forgotten how much it is. It's maybe half a meter. So you just do Google search, okay, show me where RIKEN AI is located. It's as much as moving the whole car by half a meter. So we really, really need to think what we are doing. So what's the solution? The solution is to match your tasks. So you need to be specific. You need to fine-tune your models. You need to make them smaller and more specialized. So in that sense, the neural networks have long been developed as brute force, huge feed-forward models. Then convolutional neural networks came to rescue. Instead of having huge model which can grow only bigger, more memory, more computation, Professor Fukushima here from Japan introduced convolutional neural networks in the form of neocognitron. And the idea is that you're searching for patterns in data. Because if data has some structures, then there's some patterns. So you should find those patterns in data independent of their orientation, position, and such like. So that's the role of convolutional neural networks. And basically, a simple model is the handwritten digit recognition, where you have a convolutional layer, activation layer, max pooling. It's not exactly a layer, so stage. Convolution, activation, pooling. So each layer in convolutional neural networks has convolution, activation, pooling. Okay. And with that, then you can tackle many, many problems like they did initially in the ImageNet back in 2012. But today's standards, ImageNet had only 60 million parameters. But today's standard does basically not much. But still, it was able to do many things. Now, it happens so that we all work in multidisciplinary problems. And often a colleague tells you, okay, just give me your data and my neural network will make sense from your data. So once I gave 1.3 gigabytes of EEG data to a colleague, and after 3 months, he came back to me, he says, my neural nets couldn't do anything, so your data is wrong. So I'm sorry, but the data is good. So let's think about what we are doing. And here's a typical mistake, because when solving engineering problems, people typically do not take into account any domain knowledge you may have. And domain knowledge is critical not only to make your networks interpretable, but also to make your solutions small. So here's something from a research paper. And I masked the authors and the title and so on, but they're well established. So they were looking at this simulated driving task, whereby they put an EEG cap on somebody's head and the person was driving a car simulator for 2 hours. So, and here's the time frequency spectrogram of the EEG. And their hypothesis was that as the time went, the person was getting fatigued. So the 10 hertz in EEG was getting elevated, the alpha band. You can see that time is horizontal, frequency is vertical. You can see that here's yellow around 10, and then as the time goes towards 2 hours, you have red. And they concluded with the accuracy 99.5% that they can detect fatigue in car drivers very, very accurately. Now, when you look at it with domain knowledge, whoever has ever recorded EEG knows that, for example, here, the signal-to-noise ratio is yellow to blue ratio. Blue is the background. So they used wet electrodes. So there's a conductive gel between the electrode and the skin. So in those 2 hours of driving, the gel was drying out. As the gel is drying out, the impedance between the electrode and skin increases, which means there's more white noise produced. So if you look here, it's pretty clean there in high frequencies, so blue. As the time goes, it becomes yellow. And here in low frequencies, 10 Hz alpha, from yellow to red. So basically the signal-to-noise ratio here at the beginning, yellow to blue, is same as red to yellow. So what those people were doing, they were modeling how the gel was drying out. The experiment had nothing to do with neuroscience. And that's very, very typical. So of course, in this room, in this community, that's not possible to happen. But the research publications are full of such examples. So this is why there's a certain AI chasm in healthcare. For example, this is again from MIT Technology Journal 2021. Hundreds of AI tools have been built to catch COVID. None of them helped. There's something even more interesting. And this diagram is from a colleague from Oxford who is a medic. So in 2022, he searched the PubMed for repository. PubMed is a repository of medical papers for anything tagged AI. So he found altogether 136,000 articles with index term AI. So 140,000. Now that's wonderful. So how many of those results are being used in practice? So out of those 140,000 articles, only 81 were clinical studies. Okay. Out of 81 clinical studies, only 10 had randomized trials. That's important. Only 9 were prospective, meaning following patients afterwards. So how many of these really are used in the medical services? So not many. So that's the problem with current AI hype. Out of 140,000 articles in the repository, only 2 or 3 are actually rigorous. And let's look into that. So one reason is, for example, everybody is using smartwatches, or many people are using smartwatches. I don't have a smartwatch. because you can record some health-related data. For example, you can record photoplethysmogram from your wrist. And the results are whatever they tell you. The results are not accurate and you cannot trust them. The reason is the wrist here has the worst, perhaps, is the worst site for recording PPG. So this is a real experiment in my lab. We recorded PPG from, I don't know, 10 locations. The strongest PPG is on the finger, and maybe the weakest is on the wrist. So they have chosen to use PPG from the wrist because it's convenient and because they can sell watches, not because it's the best location for PPG. So with that weak signal, you need then huge AI to extract anything from data. So it's basically a vicious circle. We want AI to be smaller, we want it sustainable, but with weak sensors, you do something else. I'm specializing in AI for hearables, which is in-ear sensing of physiological function and neural function. You see that PPG in the ear canal is very, very, very strong, almost as strong as the finger. Okay, so some facts about the AI. So making an image with generative AI uses as much energy as charging your phone. We know that. And a lot of AI is basically produced heuristically, and then people reverse engineer it to try to find some brain-inspired explanation. However, the brain is a huge, huge computer with 100 giga neurons and 1 peta synapse. Yet the brain expends only 20 watts of power. 20 watts is less than that LED light here. The neural net, artificial neural net of the same size, will be expending about 8 megawatts of power. It will have same size, but not same power. And that's basically, given that today we spend maybe 4% of electricity on digital devices, it will be 20% of electricity for digital devices by 2050. We have to think a little bit about what to do. And so the solution is approaching AI with an engineering mind. So can we use domain knowledge? Can we use engineering mind to make AI solutions which are cheap, interpretable, and which make sense? So indeed, engineers are not really copying nature. So we have produced airplanes. So we have not produced airplane to flap the wing like a bird. The airplane is aerodynamic and we have put 2 powerful engines. So it's not nature inspired. So, and Michael Jordan actually wrote in 2019 in an article, AI, the revolution hasn't happened yet, that by approaching a problem with an engineering mindset, AI can be considered as a new human-centric engineering discipline. So at Imperial, I am a director of IDA lab. IDA stands for Artificial Intelligence and Data Analytics. And our motto is that no data is bad data. No data is bad data. You can always infer something from data. Even if your data are only artifacts, you can infer that somebody was blinking or walking or talking or whatever. So no data is bad data. Moving forward, I'll talk about some misconceptions in the interpretation of convolutional neural networks. So most of you are familiar with matched filter, but all of you are familiar with cross correlation. So matched filter is a cross correlator using in radar sonar communication. So you emit a template signal, like here some chirp, it hits from a radar, hits some object, it comes back, and your received signal is polluted by noise. Because you know the signal you sent, you cross-correlate it with the received signal, and after some delay, you see a peak in the received signal at delay t naught. So that peak corresponds to perfect matching of the template and the received signal. So the only the only sample out of the cross-correlator that you are interested in is the maximum and the location of that maximum in time. You have no interest in any other sample because that maximum gives you the maximum cross-correlation, the time delay, multiplied by speed of light, divided by 2 because it goes and comes back, and that's your distance. Okay, so let's see what happens on a simulated example. So we have, again, some chirp, and this is the cross-correlator, you see. There's nothing happening at the bottom. Now the chirp hits the template, and you have basically a maximum bang. So I have detected my signal. I can do the same for signal in noise here on the right. You see, blue is signal plus noise. I cannot see my signal, but I have my maximum here. So my maximum is exactly the position of my signal. So the only sample, again, that I'm interested in is this maximum and the position. The rest I have no care. I don't care about. How do we use that? Well, pretty simple. So now play the correlation versus convolution. So the common belief is that convolutional neural networks perform convolution to find patterns in data. Whoever has done any linear system signals knows that convolution will never find a pattern in data. It's not designed for it. Convolution is the operation of a digital filter, and it can do low-pass filtering, high-pass filtering, removing 50 Hz, 60 Hz interference. But convolution does not find pattern in data, while cross-correlation, as we have seen, finds patterns in data. So here I have same chirp as before. In green, I have cross-correlation. In red, I have convolution. With cross-correlation, I found pattern in data. With convolution, I haven't. So this is same thing at minus 11 dB. So I've added noise here. And again, with convolution and with cross-correlation, match filter in green, I've found pattern in data. With convolution, I haven't. So what is that convolutional neural networks do? So what they do is they use convolution to calculate cross-correlation. Because the cross-correlation expression is here, matched filter. You have xm, w is pattern, n plus m. Convolution, w, n minus m. So in convolutional neural networks, if you look at implementation, typically they have flip. So they flip the kernel prior to convolving. So what you do is you pre-time reverse the kernel, then you time reverse it in convolution, in effectively calculating cross-correlation. So that's what happens. Okay, let's see how it works. So I have now two random, so far I have had one pattern. Now I have two random patterns, green and blue. If I want to see if there is the blue pattern in here, I time reverse it and I convolve. And clearly, so blue has nothing to do with the green, so there's nothing here. So blue convolution to do cross-correlation gives you a maximum at the position of the blue. Same for the green. So to see if there is a green pattern in my data, I time flip my pattern, I convolve the whole thing, and clearly I find the presence of the green pattern here and nothing really for the blue pattern. So hey, so convolutional neural networks are convolution, activation, pooling. So the convolution part is a matched filter, and that's what they do, because matched filter finds patterns in data. Convolutional neural networks find pattern in data. So this is what they're doing. The next thing is ReLU, the activation. So to find the maximum of my cross-correlation, I don't really need negative samples, because the only sample I'm interested in is the maximum and its location. If I pass the output of the blue matched filter through ReLU, I just get positive samples. My maximum remains. Same for finding the green pattern. I don't need negative samples to find a pattern. So here I have the green sample. So convolution plus ReLU is a matched filter. How about pooling? If I want to find this maximum, and the maximum is the only sample I'm interested in, I can split the output of a convolutional kernel into segments. So for each segment, I can find a maximum. And of course, then I'll find the overall maximum. So if I split my output of ReLU into blue segment, red, green, whatever segment, and just plot the maxima for each segment, I have sparsified my data, and I have found the maximum. So this is called max pooling. So the whole convolution activation pooling chain is a matched filter. Okay, now if you are convinced, we can do some imaging. So many students, every single student in computer science, electrical engineering, statistics, mathematics in the world has been playing with the MNIST database of 100 digits. So basically you have the input, you have some convolutional neural network, and you classify those digits. Now, here I'm using only one layer convolutional neural network. Now, and my kernels are same size as image, so I think 28 by 28. Now, when I initialize my kernels as random numbers, after convergence, they converge to that. So, okay, so I initialize kernels with random data, and they converge to 0, 1, 2, 3, 4, 5, 6, 7, and so on. So what am I doing? Because I have domain knowledge. I have 70,000 digits. So 60,000 are training and 10,000 are test. So I'm pretending that I don't know what I'm looking for. It's not true. I have domain knowledge. How about if I just average 6,000 training images for each digit, 0, 1, 2, 3, 4, 5. And I initialize my kernels like that. So after convergence, I converge with something very clean. So even a single layer convolutional neural network, when you initialize your kernels based on domain knowledge as average of your training data, gives you 90% accuracy. While if you initialize them randomly, the accuracy is 82%, and the training is much longer. Okay, now we go to the sign language, which are more complicated images. So there's a sign language for deaf people of letters C, E, K, L, and so on. Same thing. So if I do nothing, I just put averages of my training data, and I don't train my network, I use them as cross-correlator. The accuracy is 52% without any training. Because I have 10 categories, the chance is 10%. So by just using match filter, like in radar, I don't need a network. I have accuracy 52%. If I initialize my kernels with the averages of these, like that, and then train them, so they converge into that, and my accuracy is 95%. So even a single layer network, when you use domain knowledge, can give you very high accuracy. If you initialize as random numbers your kernels, they converge to something that has absolutely no interpretability. The accuracy is 39%, while your kernels initialized by matched filter, so each of those kernels has physical meaning. It some sort represents the sign you're doing. So not only the training is much quicker, but also everything you do is interpretable, very much like here. So you converge to something, each kernel here is interpretable. These are numbers, so I know what I'm doing. And that big obstacle towards using CNNs in critical applications is overcome. Same thing happens if you have, say, two-layer network, and now my kernels are smaller. I've taken patches from those averages. So by doing so, the accuracy goes from 90% to 97% for my domain-informed initialization, while for random initialization goes from 82 to 67. It goes down because it's data hungry. It wants more layers. Okay, going forward. So a lot of that has been written in the last 2 years, basically. So this is an article we wrote in IEEE transactions on system man and cybernetics. Same for graph neural networks, so interpretability through match filters. here's one application. So I told you that I've been working on hearables, which is in-ear sensing of EEG, ECG, blood oxygen level, blood glucose, temperature, respiration, many things like that. So my device has basically electrodes for electroencephalogram and electrocardiogram, has a PPG sensor for sensing respiration, blood oxygen level, blood glucose, has accelerometer and such like to deal with artifacts. And those artifacts can come from maybe walking, talking, chewing, and so on, so on, so on, so on. So what I would like to do, the ear is not a very good location for sensing electrocardiogram. Yet chronic diseases, heart diseases are very prominent. In fact, cardiac diseases are the biggest killer. Now, this is why we put ECG sensors here. In order for the signal to travel to the ear canal, it has to go through empty cavities like windpipe, mouth, sinus. So it gets attenuated. Now, instead of using brute force to extract ECG from such signals, let's think a little bit. So let's use some sort of encoder-decoder network. So I would like my input to be ear ECG, and I would like my reconstructed output to be clinical quality ECG. To do that, we do something called core encoder, which is introduced in our team. I'll not talk much about that. What I'm going to show is again, so we initialize kernels in the autoencoder first randomly. So this is random kernel, which is then gradually being trained. And you see that with training, and training can last forever, it gradually adopts the kernel, the shape of ECG. But how about if I initialize my kernel with ECG? Because after all, I know I'm estimating ECG. Why am I pretending that I don't know what I'm doing? If I initialize my kernel as ECG, it just changes very slightly. It converges to a kernel, much quicker than from random. So by using domain knowledge, you can do a lot. You can have a very small network which can do wonders. So this is, again, from random initialization. This is by initializing with real ECG. Not much difference. So why wasting computational resources? So with that, then we have developed this so-called core encoder. The input is in-ear electrocardiogram. The kernels are initialized by a real electrocardiogram from chest. And these are real samples that are shifted in time and so on and so on and so on. Okay, after training, we can basically see that the top is reference chest electrocardiogram. The middle, if you can see, is very noisy ear ECG. And the bottom is R peaks from ear ECG. The system is updating. This is all in real time. And this can be performed with a microcontroller of any wearable device. So it's very small. Why? Because you use domain knowledge, you are interpretable. More so, here's the principle of the core encoder. So this is the electroencephalogram. So this is the EEG. And if you record EEG from symmetric locations, then maybe you can capture some traces of electrocardiogram. By using these interpretable domain-informed networks, which are small and initialized with real domain knowledge. So this is here the electrocardiogram, which is extracted from the electroencephalogram. You see the excellent quality ECG extracted from EEG, from a small network. Okay, what are we doing now? We are doing something on heart GPT, and something we are hoping to do with Professor Tanaka, who is here. What else we are doing? We are doing a lot of tensors for, say, compression of LLMs, interpretable transformers, fine-tuned models, which are basically, my first slide showed that we can reduce energy by 30 times if we fine-tune models, especially for finance, FinLama. Compression, deep networks, but Tucker layer. We're also interested in how the knowledge is represented in LLMs. Has has AI been overhyped? Well, this is my first book on recurrent neural networks for Wiley, the blue, in 2001. It was published in Wiley edition on adaptive learning system. By the time I published this second book on neural nets in 2009, also for Wiley, my first book was advertised not as adaptive learning system, but machine learning. By the time I published this work with Dr. Qibin Zhao and who else is here, Cesar Caifa, on tensors, and then that led to a book with Andrzej Cichocki and Qibin on tensors. My first book was advertised already as artificial intelligence. So it's same book, same edition, which moved from adaptive learning system to machine learning to artificial intelligence. By the time I published my recent book on data analytics from graphs, my first book became, I don't know what it is, general artificial intelligence. So it is overhyped. So let's stop overhyping what we do. Let's employ engineering knowledge. Because here's the danger, this is my last slide. We must use domain knowledge and not brute force when doing AI. So Google has signed contract to buy 7 mini nuclear power plants to power their computers. They need to power their computers because they have huge models. They have huge models because they're using brute force. Because the DeepSeek, Chinese startup, basically beat the ChatGPT with much by using reinforcement learning and mixture of experts and so on. So you need to use your knowledge. Amazon, same, they're buying nuclear power plants. One of the founder of this modern generative AI, Ilya Sutskever, he recently said that, well, we have to stop using vast amounts of data. We need to use our knowledge, and it's up to us to do it somehow. Thank you very much.
Thank you for the interesting talk. Any question, comments? Maybe we have time for 1 or 2 short questions.
Great talk, very interesting. And I'm concerned that your match filter is very good concept. How this match filter relate to the multi-layer? For one layer, it's easy to see the convolution. And with multi-layer, and how can explain this kind of filter, or okay, so hierarchical one, or?
So I have shown that a little bit, but maybe I went too quickly. Mm-hmm. So this is for, say, 2 layers. So you take match filter and you need little patches. You snap a little patches from your match filter. And these are your new smaller kernels, like here. So these are parts of MNIST numbers, small patches. And it works even better. So accuracy goes from 90% for single layer to 97% for double layer.
Yeah, thank you. Any other question? Maybe one question. Who?
Yeah.
Okay, please. So you mentioned that all data, even the bad data, is worth to use. So do you have any comments? Is any special technique to use all data?
I do. So for example, here we have EEG. And in blue, somebody was just doing nothing. In red, somebody was reading a book. In yellow, somebody was chewing food. And in purple, somebody was walking. Okay. And this is the microphone, the microphone or accelerometer on my device. When somebody is doing nothing, there's no movement. When you are moving your mouth, because the ear moves a little bit, there's movement. When you are chewing food, there's a lot. When you're walking, there's nothing. So here it is. So I can use the microphone signal here as a concept as a proxy to digitally remove the artifact. Normally, I would have to throw away those epochs. But because my microphone or accelerometer has a proxy to the movement, I can digitally remove them. And the second thing is you can infer behavior of person. For example, this is EEG, ear EEG. When somebody is chewing banana, This is EEG when somebody is chewing grape, ear EEG. Ear EEG, somebody drinking Coca-Cola. Ear EEG, somebody is drinking water. They're all different. So even if maybe my denoising sometimes is not that good, I know I can classify this. These are different patterns. I can tell, hey, somebody was eating banana or eating bread or eating rice or chewing grape. You can even, because you know how many calories there is in those bites, you can even know how much about the calorie intake of a person. So no data is bad data.
Thanks.
Yeah, thanks.
Yeah, because it's the time, so let's thank the speaker again.
Thank you very much.
Yeah, thank you very much for the interesting talk.
Very glad to be here, and thanks, Professor Dr. Qibin, and invite me here to see many old friends. My previous colleague, Danilo, and Zhao, and many others. So today's talk will be give your idea about my group's work towards the variable inference based on disentangled tensor manifold, because Qibin's group working on tensor learning. So in my talk, I mainly focus on the tensor representation. In this talk, I will first, so how to represent data into local tensor manifold. And the second one is how to implement this local manifold by using disentangled information bottleneck. And the second one is learn how the knowledge large language model can be used for learning the causal inference, and then give you some applications. So first things is, what is the motivation we're working on this tensor representation? As we know that now we are in large model era. Everyone talk about large model. And what problem the large model still exists is that although large model can solve many problems, but there still leave some challenges. First challenges is that unexplainable, that is the inference result is not variable. And also weak OOD generalization and hard to control, because now we are mostly to use generative AI when we generate data or image or video, and it's not easy control the attribute or the post of the generate data. And still another is that hallucination problems. So this is the big problem. Let's see one simple example. I try large language model, for example, to ask to generate data. First picture is that please draw a picture that goalkeeper jump up to save ball. And then what come out is that there is 2 balls there. Why? I don't know that, because, but in the real data, actually do not have this situation. But I still want to control this situation. I ask delete 1 football in the picture, and then they generate, okay, only 1 ball, but the image is complete different. They regenerate the image. So this is that the model cannot easily just control by prompt. So there's still another example is I just asked to draw a picture that football player passed ball to his teammate, but you see that it's not pass ball. It's just dribble the ball. It's not really pass. And what this means this means that it's almost the state of art of generate image. This is just general image. For the video, the situation even worse. There is generated a lot of unreasonable data. So what this happens, and we are trying to explore the problems. The first problem is that for AI, it's really variable problem. For cognition, for the perception problem, actually is the problem of semi-suitable problem that cannot decide. For example, I just give one example that the input of this, just for input is a big image. And then by using CNN model to embed it a vector y. Of course, the image is much big, higher space. The embedded vector is still very lower dimension. For example, 1024. And for image size, for example, is 256 multiplied 256 is already, the dimension is already something like 65,000 dimension higher space. So once in this case, y is given, and then the last layer is the fully connected layer. If we input a face image, and then y is represent a face image, and then we use fully connected pattern match to classify. The problem is the same face vector may have original space, image space will project to the same face vector. So all these data project to all original data project to this y, we all classify as a face. Because for CNN model, the last layer is only just fully connect and softmax. So this is why once the image giving a small data noise, small noise, and then they will completely change to classifier to others. So this is the problem, and we are trying to solve, give some explanation for this. First things we try to explain this from representation point of view, that once we have the embedding vector, the embedding vector actually have different components. One component is related to the discriminate. For the embedded vector, we can decompose them into three parts. First part is discriminate part that used to classify object, for example, the face or non-face. And the second part is attributed part. For example, the hair color or the expression, its smile, not smile, is not related, it's not directly related to classification result, no matter how you are smile or not. And the third part is the pose part. Pose is which direction your face, and so the embedded data will have these relationships, and how we can use these three parts. First, for classification part is only first part is enough. But for the second part, for example, the pose part, we can use to verify. And we can ask, you see that this is the face. This is classified as face. And then why? You can see that, okay, your face, you have 2 eyes, 1 nose, and you are facing, direct face in front, and this. So for the representation, we can represent the discriminative part and attributive part, and also the post part. And each part can be represented into the tensor case. This is what we want to learn, the tensor disentangled representation. So what kind of method we learn this tensor decomposition? And previous Qibin and I work together. The rank 1 tensor decomposition will give a very good model, that this model will provide us automatically determine the rank of the tensor, and this will help us to determine the, for example, the how many dimensions we use for classification, and what part is represent the post part or attribute part. And this I will not go detail. And the second part is, once we have a local tensor representation, if we have a local tensor representation, and how they connect together. And this is by using tensor manifold connection part. That we have a local tensor representation here, and how this representation move to the nearby tensor localization. And we need to transfer this tensor to next tensor, and each component, rank 1, how they transfer to the second one. And we need to learn this connection. And so by learning lower dimension case, and then we can provide more robust learning of this. And how we learn this is the second part, by using disentangled information bottleneck. As we know that information bottleneck, this model, the first one model, that try to learn a discriminative T that has a minimal information with X. So here is the representation for input X. T is the minimal information with input, and then maximize classification result. Okay, the T is called information bottleneck. But we know that once we using this information bottleneck, we usually use this cost function, and beta and B is the coefficient we need to adjust. But we found that the real solution will satisfy the following result. That means the information bottleneck vector does not represent the most complex lower dimension solution. So we propose disentangled information bottleneck. And the cost function is look like this. Actually, it's another idea about Danilo's mentioned, that the data, no data is bad data. They are useful. So X is input data, and we are trying to represent the information bottleneck T and the irrelevant part. But the cost function is that we try to decompose this part, and also try to minimize information between X and Y, and try to maximize this part. And what this part use? This part actually is used for verification. Try to, if the data X input classified as face, and then we use this pose or attribute to verify the result. And this is what we try to do. And by using this new cost function, we develop algorithms for implement these minimization problems. Each part, I will not go to detail. If you are interested, and we can provide you the original paper to read. And not easy to explain this equation in detail, but each term we can have a lower bound cost function. And then by minimize this cost function, and the third part, this part is replaced by the we call adversary loss. Try to minimize this cost function by using adversary loss function. And the previous two is using lower bound. From the testing result, and we'll see that the performance by using disentangled data provides much improved result. And this is the first part, that using disentangled information bottleneck. And the second part is how we constrain the representation data into a submanifold such that the inference will become much more reliable, because we already know that the example that for the panda plus a very small noise, and then you will classify this noise data could be classified any other result. And why this happens? That because in very high dimension space, two data, the distance is almost the same from statistically. Two images, because they are all far from each other. So with a very small noise to the image, and then if you just measure the distance of two images, and then they are probably very fast. So directly measure the distance matching these two parts is not a good solution. But if we project this data into a small manifold, that each object has its own manifold, and then we first test if the data belong to this manifold, because this manifold can have attribute dimension and also pose dimension, and we can test the classifier object by checking if they belong to this submanifold, and we can provide the classifier by checking the data belong to this submanifold. This is the main ideal. And in order to do this, we introduce two basic structure to reflect the data. First part is introduce called alpha structure. The alpha structure is that if we have project data into the manifold, M is manifold, and then the alpha fold, that means if the partial derivative or the frame, the coefficient in this manifold in the tangent space is the same as if we just project one component Z, keeping Zj, but letting others to 0, and project this manifold to this manifold, and the same we get the same coefficient, same coordinate, and then we see if this function f satisfies this condition, and then we see that the manifold and f are alpha correlated. What this means that if we see that Zj is independent, and then they will have this result. They will have this result. If the alpha, the manifold alpha satisfies alpha relate to M, and then this manifold is identifiable. Oh, sorry. Okay. So I may go to two details, and just second part is we try to introduce another structure in the manifold, is that beta structure. Beta structure is that two coordinates in the manifold, they are orthogonal, that the component mathematically represent in this way. And what geometry interpretation is that we can found some coordinate that represent the phase shift and the head lift up or down, and then by introduce the beta structure. And also can implement this beta structure by using disentangled model. And I will not go to detail and just provide you some other results due to times. And the second part is we called that large language model-based causal inference for some specific VQA problems. And you may know that VQA problems, because related to the text and the video, and sometimes not easy to alignment them together. So what is the strategy we use? That we are trying to use the causal inference strategy by using front door adjustment values, and also introduce the proxy variant. And the model is the following one, that adjust front door adjustment and try to check the question answer is correct or not. And so this need to use some common knowledge in advance. And this is the first work. And the second work is that the common knowledge is easy to learn, or easy to learn from the large language model, how to decompose the general description of the problem, to decompose them into very fundamental problems. And this is the second part is VQA-based language-centered tree reasoning. And we proposed some work on this by introduce verbal inference of VQA problems. And still another one is that we are trying to use controllable data method to the problem of virtual closing try-on problem. This is a very large demand in online shopping, and try to use online the virtual try-on and attract people to buy clothing. Okay, this just provide you some models. And so here it gives one simple example where some company has implemented in our work. For example, this one is that we are just use very smooth, try to close, keeping this object and change the background, and then the video will automatically change into the new site by this video segmentation. Okay, some work, and you can find some open source, and one open source work, Liqing, and it's very popular work, and Amazon already implement their work in their platform. Okay, that is all for today's talk, and I would like to thank my colleagues, and they do contribution in this work. Thank you very much.
So thank you very much for the interesting talk, particularly for the last example. So any questions, comments? Yeah, please.
Thank you very much for the very nice talk. Yes, I have a question. You have shown an example of an adversarial attack to the Panda image, and the representation in the manifold. So my question is, have you tried to develop a purification technique as a protection for adversarial attacks using your manifold projection or some of these ideas?
Okay, that is very fundamental question. This question cannot be solved completely, but we are just trying to reduce the error or error performance, because once we change the object manifold, for example, for face manifold, and we will have each one dimension is the person, and some other dimension is the pose and attribute. And once we try to, for example, recognize face, and then we will project the data into this manifold and try check their attribute is belong to their dimension or not. Just try to improve, but this cannot be complete solved, because for perception problem is not complete decidable problem. Yeah. Okay.
So thank you. Any other question? Yes. Professor, may I ask a question? So, in your work, have you ever considered the manifold you learned can be kind of dynamical? It will be changed maybe with some.
Yeah, it's for some data may change. The data adapted.
Yeah.
Once new data come, and then the manifold will also change. Right.
Yeah.
Right.
Okay, thank you very much. Any comments, question? So if there's no more questions, so let's thank the speaker again.
Thank you.
Okay, thanks for the invitation. Actually, I come to the RIKEN almost every year because RIKEN and our AI center, CFA, called Center for Frontier AI Research, has a very close collaboration. So we have the MOU. So that's why we have the exchange programs every year. So fortunately, I will visit the RIKEN again in this November. So by the way, I come from Singapore, public agency, government agency, called A-STAR. A is stands for agency, and S stands for the science, T stands for technology and research. So I think in some sense, the A-STAR is the counterpart of the RIKEN in Japan. So our AI center, the CFAR, is also very similar to RIKEN AIP. So in this sense, so my name is Zhou, Tianyi Zhou. So you can find everything about myself at my homepage by searching this name. And this is my kanji because this talk is to our dear Japanese friends. So I also write down my kanji here. Sorry, should be pronounced. I'm not so sure. Shu Tianyi, right? If there's a Japanese friend who can correct me if I'm pronouncing it wrong. So today I'm going to share some of our recent work. Actually, this work is very recent, but we haven't published yet. But I think it's very worthy to advertise to more public audience. So it's related to LM uncertainty estimation and application. So this topic is quite hard. So, but we are very confident to say so. We have provided a different angle or different perspective to see how we can estimate LM. Okay, because I came across many friends for the very first time, I will still allow me to give a very short introduction by myself. Actually, I graduated from Singapore Nanotechnology University in 2015. So after graduation, I joined the Sony. So, but unfortunately, it's not based in Japan, in USA, California. Sorry. But after 2017, I come back to Singapore and joined the A-Star. So, but from 2022, actually, we founded the AI center called CIFA and take a role of the deputy director. That's my whole journey. So I'm personally interested in two domains. The first part is how to improve the efficiency for ML systems. The subtopic is like the transfer data set condensation and the model compression and so on and so forth. The second part is about how to improve the trustworthy interpretability about the machine learning algorithms, and which includes the adversary robustness, model bias, and LM uncertainty. I'm going to introduce about this part. So I do a lot of academic service, including, for example, 2024, I was a workshop chair for CAI, this international conference on AI. Actually, our AI center initiated this AI conference in Attribute Society. And so I got support from 4 Attribute Society. And this year, I also take a role of the industry program chair at IGCN, and also the associate program chair at IJCAI. So that's why next week I will fly to Montreal. After Montreal journey, I also need to fly back to Guangdong. So we have the satellite in Guangdong. I believe you have the submission, you know this one, all right? And also, I was nominated by the general chair to take a role of technical program chair in IGC in 2027. So that's my whole checkpoints and something I want to share with you. So let's drop to the key content of this talk. So the first question we want to ask is why do LLM need uncertainty? So I'll give you 2 examples to industry why. The first, so this is the, as we all know, LLM produces the errors. Technically speaking, if you borrow the technology, we call it hallucination, right? So uncertainty can eliminate the or can characterize the reliability of the model output, thereby indicating that the probability of the model output is wrong. There are 2 examples here, okay? How the LLM uncertainty help us to detect the hallucination part. For example, the vanilla chat system, I believe everyone is using the ChatGPT or other foundation model to help you to get some answers, right? For example, this is a very famous example. So which number is bigger, right? So if we based on the memory-based LLM model, actually we tested the 2 foundation model. One is from the Baidu company, another one is the Llama from the Meta. Okay, unfortunately, without any notification, without any of the alert about these answers, probably if you have no common sense, you have no basic understanding of the mathematics, you probably just easily to think this is the correct answer, right? So once uncertainty estimation, what happened? So we can come up with uncertainty-aware system. So when they produce the answers for the questions, we probably can highlight some very important words. For example, the bigger is a very important word. With a confidence of 0.7, 0.76. Actually, this 0.76 is not very high. Normally, we only output tokens or below, no, above the 0.998 or 95 something. So at least at 0.9, we should output a token. But below the 9, we think is low confidence. So with this capability on LM uncertainty estimation, actually you can create an alert to the users. Actually, we're not so confident about to produce these answers. Okay, let's further extend this more applications. This is for the single agent. Of course, more and more people are is aware of the multi-agent system. This is the vanilla multi-agent system. If some node actually has collapsed, produced some mistakes when they interacting with other nodes, other agents. If there's no way to alert, there's a potential toxicity in the communication, what happened? The errors or mistakes will be propagated, will be further exaggerated during the communications. So finally, the answer will be inevitably to be wrong. Okay, but with the uncertainty estimation, what happened? We can probably identify the risk to block the delivery or RAG enhancement. These are potential applications. That's very important. We can say which node, which agent possibly produce which answer may be wrong. You should rethink about the answers before delivering to other agents. So the multi-agent system, that's also very important. Okay, so the second question we want to ask you about is does the traditional probability-based method still work? Okay, to answer these questions, I probably give it the definition is that the uncertainty characterization methods represented by max class probability provide reliability assessment for traditional classification tasks. However, the LM is particularly of the generation this kind of tasks, right? A deep generation, and as we know, is totally different from the classification task. So makes the maximum class probability no longer applicable. Why? Give me some examples. So this is a traditional classification problem. So for example, this is input images. We input the deep learning, even for deep learning. Okay, we can generate the probability for each class. So simply we can say we are very confident to say this image should be marked as a reliable label as a dog here. Okay, but for the other, this one, right? Actually, it's not a little bit trigger, right? But the dog is not so clear. So that's why the probability drop a lot. So in this case, we probably can say we have low confidence to say it can be marked as the dark. So maybe the confidence is quite low. So this is for traditional classification model, but for LM, it's totally different. Okay, let's look at however. For example, the user probably will ask this question: would you please give me one name of a U.S. president? Okay, sure. There's a historical American president. So all these answers are correct. Barack Obama, Abraham Lincoln, John Kennedy, right? All these answers are correct. Are potentially should be the correct candidates for this type of the questions. So you can see. We test out the Llama 2, right? You can see actually all the correct candidates, the probability are not so high, okay? Because at this point is we call it a common knowledge question, a common knowledge question. So the model actually knows, but it's marked as unreliable. So we're not so confident which one should be the correct answer. So many correct answers here, right? Let's look at the other examples. For example, you probably can ask the very challenging questions like this one. Will be the future evolution of the observed universe ultimately lead? The element will output the answer like this way. The universe will eventually go to the heat death. There's very high confidence. Actually, unfortunately, this type of question is quite challenging. No one on this earth, in this earth, can have the very confident to say our Earth will end with the heat death. So in this type of question, we call it is the real internet and speculation. The model doesn't know, but it's marked as reliable. So it's totally different. Okay, the generation AI. So let's come to our third question is what does a good AI uncertainty estimation look like? How do you think? Right? Just I mentioned the traditional probability we cannot we cannot use anymore, right? Because for classification problem, for generation task, we see so many difference between the generation and the classification problem. So I think there should be two characteristics when we consider what kind of metric should be used for AI as uncertainty estimation. The first one is this kind of metric should have a capability to categorize the relative relationships. What does it mean? It means that when generating nested token, among all the possible token, you should tell us which one is more likely to be correct. That's called the relative strength of the evidence. By the way, the evidence definition is here. The measure of the amount of support collected from the data in favor of the sample to be classified into a certain class. That's called evidence. That's called evidence. Okay. So, for example, this figure shows that the very first token is much more confident. It's more likely to be correct compared to the second and the remaining tokens. Right? That's called the relative strength. That's the very first characteristic we want to have in the LLM system, especially we want to estimate the LLM uncertainty. What's the second one? Second one is that the LLM uncertainty estimation mesh should has the ability to categorize the absolute relationship. When generating nested token, the knowledge of whether the model is sufficient, has the sufficient knowledge to make a correct answer. That's called the absolute strength of evidence. Can you tell the difference between the relative strength of the evidence and the absolute strength of the evidence? For example, this figure, right? There's so many columns. It's above the threshold, which means that I tend to believe there are 4 possible correct answers, right? So, but compared to the first one, even though this answer is dominant, more confident than the remaining tokens, but the evidence, the strength of evidence, still below the threshold. So, which means that you're overconfident. That's the issue of overconfidence. You are making the wrong prediction. You are generating the wrong tokens, even though this evidence of token is much more higher than the rest one. Okay, so the good one should have these two capabilities. It's able to categorize the absolute as well as the relative strength. Okay, so let's come to our fourth question or third questions. Why did the absolute evidence of information disappear? Why we cannot use the probability-based method, right? So because of the normalization process. Because the normalization process requires the sum of all tokens shared probability to be 1. So which results in the loss of the absolute strength of evidence, so making it impossible for probability to accurately characterize the uncertainty. So the root cause is because of normalization. Let's see 2 examples to see why. What's happening inside. For example, this first scenario, if we have the logic output in deck this way, right? This is for first scenario. The second scenario in this way. After normalization, this type of the distribution will become to this. This type of the distribution become of this. But come back to the evidence strength. Which one we should trust more? The very first one. Possibly have the 4 correct answers. The second one, even the first one, is much higher than the remaining token. We cannot still trust the first. But after softmax, after normalization, what happened? The situation becomes the reverse, the opposite one. The system will trust this will be the correct answers, not this one. Even the original logic or original evidence strength is totally different. Okay, that's the very first of the scenarios. The second, that's called the evidence strength is lost during normalization. The root cause is the normalization. Let's look at the second distribution. For example, this where, for example, how the Earth will be ultimately lit, right? That's kind of the where real situation questions. So we look at the largest distribution. What happened? Many answers, right? For example, many answers we don't trust too much. But this one, evidence accumulation, this common sense one, we have the 3 answers we can trust a lot. But after normalization, actually this real situation and the common scenarios actually generate the same probability distribution. That's not something we want. We should differentiate between the first real situation and the common sense. If the system, if LLM has the common sense, you should deliver the confident answers. But after normalization, they get the same distribution. So lost. Evidence stress lost. That's the root of cause of the why LLM generate the hallucination, generate the mistakes. Okay, so new idea, how to resolve this issue. So we come up with the uncertainty estimation based on evidence. Actually, this evidence theory is coming back to I think more than 70 years ago. But we look at this evidence theory. We found it very useful in this context of LLM. So the traditional one, the probability. When you ask a question, the model will generate 2 high probability or low probability. So in other sense, we can interpret in this way. We don't know answer. We know answer. We don't know answer. We know answer. Depends on how you set up a threshold, right? But I think that's not enough. We should further categorize the uncertainty. You don't know. What kind of you don't know? If you have for example, so that's why I divide this uncertainty estimation into the 4 quadrant chart, 4 quadrants. This is called a quadrant chart. So there are 2 types of uncertainty. So a lot of the literature review, they say just the overall uncertainty, certain or uncertain. I think it's not enough. We should further categorize the uncertainty into two dimensions. The first dimension is called AU, aleatoric uncertainty. That's a very technical term. Let me explain a little bit about it. What is the AU, aleatoric uncertainty, which means the uncertainty coming from data, coming from the question. The way you ask a question may have some multi-choice correct answers. Just reflect, right? Recap the very first question. Please list down the name of the U.S. presidents, right? So in history, so the root cause of the uncertainty coming from the data has the multiple choice. That's called AU uncertainty. The other y-axis dimension is called EU, epistemic uncertainty. What does it mean? So the root cause of the uncertainty is coming from the model. So maybe this model has no sufficient information to generate the correct answers. Even though the model trusts that his answer should be correct, but unfortunately it's not. It's not real case. So we divided the uncertainty into 2 dimensions, AU and EU. So around these 2 dimensions, we can generate 4 quadrants. The very first quadrant is called AU is high, EU is low. So the first quadrant and the fourth quadrant, we can see they basically have the very similar distribution. They have the 3 possible, almost similar evidence, right? But that's called AU is high, EU is low. So the first and the fourth quadrant is called AU is high, which means that maybe these questions, to answer this question, we should have the 4. Maybe we have the 4 possible correct answers. That's called AU. Because the way you ask question maybe is problematic. Okay, so that's called may have the coming from the uncertainty, coming from the data. We call it AU is high. How about this? This is AU is low, right? They are very confident about among all these tokens, there are 1 token should be very high chance to be correct answers. Let's look at the other dimension. That's called when the EU is high, and so for example, this quadrant 1 and quadrant 2. So we found that all this, the highest column is still very low. That's called EU. EU is high, which means that the model uncertainty is quite high. The model has no sufficient information to answer these questions. So this, you can see the highest column among the quadrant 3 and the quadrant 4 are very high, which means that model has sufficient knowledge to answer these questions. Okay, so compared to the traditional probability, I don't know, I'm so sure, I'm not sure, right? We'll further break down. So for instance, the quadrant 1, it means that I have no idea. AU is high. What is that? I have no idea. AU is high, EU is high. I have no idea. The way you ask questions is problematic. I also have the model, the LLM model has no sufficient information to answer this question. That's called I have no idea. Quadrant 2 is the EU is high, AU is low. What does that mean? I don't have the sufficient domain information to answer this question, but I can suggest one question, the first one, maybe is correct answer. Quadrant 3 is that's the best case, is that AU is low, the EU is the low. So which means that the way you ask a question, very good. I also have the sufficient knowledge, domain knowledge to answer these questions. That's something we want to generate for LLM. To some dimensions, quadrant we want to push frontier for this type of the LLM. Okay, the last quadrant is called AU is high, EU is low. What does it mean? Can you interpret? Yeah, I already explained the 3 quadrants. Can you interpret the last one? Last one is that I have no, I know there will be more than one answer. I'm also very confident there will be 3 correct answers. Right? So that's how we interpret the uncertainty. How interpret? I don't know, I know. Okay? So following this theory, or further, actually we also found that there are some previous work resonated with this idea. For example, OEDA detection. So these 2 papers published in NIPS and SML also found that using the logics can help us to differentiate between the in-domain and out-domain distribution. Another application is called the classification. Okay, so when you rotate the input image, actually the uncertainty goes high, goes low. So the previous 2 works also revealed that we possibly can use the logics to quantify the uncertainty LLM, but there's still gap between the traditional one and LLM. Okay, so we developed a theory to say why the logics can be used to categorize the evidence here, right? Amazing thing happening here. Yes, this is for traditional evidential modeling training course for classification model. Okay, this is for, you can see this is traditional cross attribute, right? Loss for classification model. This is some regularization for the evidence regularization. Okay, regularization term. So fortunately, this part is the LM training loss. So we can find that these 2 loss actually is the same. Okay, they share the same spirit when we do the further breakdown. Okay, so after mathematical formulation, the cross attribute loss can be transformed into expression that's consistent with the evidence modeling. So we can further borrow the evidence theory from the traditional classification model into LM modeling. So that's why we can use the logics to help us to categorize the LM uncertainty here. Okay, I wrap up the theory, evidence theory, in the context of LM. Now, I'm touching a little bit about how to make this uncertainty estimation applicable in different scenarios. Application 1 is the uncertainty guided dynamic decoding. So, for example, this is the user asks this question, classify the following sentence into following of the emotions. The sentence is blah, blah, blah. The class of the sentence is should be positive, negative, it should be neutral, right? That's how we use LM to help us do the sentiment analysis, emotion recognition, so on and so forth. Okay, so usually the AIM just output the answers regarding the uncertainty, right? But with our uncertainty estimation, we can set up a threshold. So above the threshold, I believe there's only one answer. That's why we can directly answer the top one. But below threshold, which means that we are not so confident about these answers. Possibly they have the two. So that's why we can sample the answer from the top two, right? So that's called a dynamic decoding, right? No matter how, so I think it's very useful. Not all the answers should be always generate the top one answers. Depends how the way you ask a question. Depends on whether this model has the sufficient knowledge. You should give some freedom to generate the outputs, right? Depends on the evidence strength. So we compare with some existing very popular decoding method, for example, top K. For example, give it some freedom, but always fix the K beforehand, before the deployment of the whole system. You should sample the answers from top K. This is for gradient. Always generate the top one answer. But our system can automatically choose which you choose the top one or choose top K based on the uncertainty strength. So which we can embrace both the diversity and the reliability. This benchmark with a gradient search top K probability based on entropy burst. We create a logic token uncertainty. So we found it's not a marginal improvement. It's a big leap actually in this decoding task. The performance is a big leap actually in RIM. So the second application, I think to myself, I pretty love this second application. What does it mean? When you open the GPT, no matter what kind of the LM interface you open, you ask a question. For example, I asked this question: what's the diabetes and what are non-prescription drugs can diabetes patient take? Very technical questions related to our body health, right? So it's the critical important because it matters our life. So this is our interface to generate answers. Different from all the existing interface, we can, for each token, we can categorize the AU, EU, and also the total AU plus EU will take an average. This is the total uncertainty mark, uncertainty score. So the generating token has the higher is more red means more uncertain happen, more reliable. You should double check. So for example, this terminology term, you should double check. Okay, right? So for example, this AU high, EU high, possibly you don't, the way you answer the questions, the way you ask the question, you probably also how to if we found the AU high means the way you ask a question is problematic, you should rephrase it or add more context and information. That's sometimes we call it context engineering. It's popular right now, right? That's how we can lower the evidence, lower the uncertainty for the AU part. For AU part, for example, this is a comment, right? Actually, we can change this comment. Even we can remove this comment. This is called AU part. AU, this token, all right, coming from the data. Multiple choice generate this token. We don't necessarily need this comment here, right? But this one is maybe the LLM backbone has no sufficient domain knowledge to generate this terminology here. Okay, you should double check it whether it's correct or not, right? Okay. Also, this glaucoma, right? EU is high, which means that the current system, the current LLM backbone LLM is not so confident, has no sufficient knowledge to generate this token. You should double check it. So we integrate this uncertainty estimation in overlay with this existing LLM models. So help the user to know which part you should double check, which part you can continue to trust the answers. This is second. The third one, we skip the benchmark. The third one is called uncertainty-based RAG. So RAG, when you use the phone, we use the RAG. You have the personal database. So the question is that we also generate a lot of hallucination because we need to retrieve from the database. So after implementing the uncertainty estimation, we can reduce the number of the retrieved calls, right? Also improve the accuracy, because we don't necessarily retrieve all the relevant information. Those information, those data points, the items, and also content we should discard, right? Otherwise, we will increase the chance of the hallucination. Okay, more application waiting to be explored. Actually, we released this archive paper. We don't have published yet, but a lot of follow-up work. For example, the HCI for MIT, and also the Mattering RAG from the MSU as a Korea University for agent collaborations. So we will have released the paper and the code, waiting for more applications in this committee to be explored. Thank you.
Many thanks for the great talk. Are there any questions?
Yes, thanks for the great talk. And yeah, I'm wondering how can we use the uncertainty estimations in the LLM to build a more adversarial robustness, the large language model? Yeah.
Oh, I think the adversarial attack defense, this type of thing is totally from. I think it totally separated the topic apart from this trustworthy one. This is more like the uncertainty. But I think there are some inner connection under the table can establish robustness and uncertainty, but we haven't tried yet. Yeah, I think it's also one of the potential applications to be explored in the near future. As also a very good suggestion.
So how to evaluate AU, EU, like the lower EU and the lower
okay.
AU is better?
I think we escape. This is a formula, AU. We just use the output of last year, the largest distribution. We can easily compute for this formula, easily compute the AU and EU. At this AU and EU, this concept is not accurate. Yeah. It's not invented by me. I just borrowed 70 years back, the evidence theory. I further categorized in the context LM. But in the context LM, we are first time to introduce the AU and EU, to introduce the hallucination, uncertainty, so on and so forth. Very simple formula.
I see.
Yeah.
Thank you.
Yeah, please.
Hi. Very nice presentation. What happened? Is it possible to have something where it's completely flat and it's just like, I don't know, I don't have any answer, and then you will allocate one bit to say, well, I don't know.
Can you say again?
Like,
very flat
here you have always one answer, at least one answer.
Well, which quadrant you were referring to?
I mean, if there would be a fifth possibility where you don't have any answer, will be?
Oh, yeah. That's a traditional way. So, for example, about this traditional way, we do the for example, the classification, right? There's a category 1 until n, right? There's an additional dimension we say we don't know, right? This is called uncertainty dimension, right?
Okay.
Yeah, that's for traditional one.
Okay,
yeah.
thank you.
But for LM, because it's a generation model, so we don't treat it as the classification one, so not necessary. Okay. I think I don't want to delay too much about the necessary speaker space. So that's all. If we have any suggestions, questions, and potential collaboration, please feel free to email us. Okay, I will follow up with that. Thank you, Dan.
Okay, let's thank Professor Zhou again.
Yeah, thank you. So good afternoon, everyone. Thank you very much. I'm very delighted to invite all of you to be here. And today it's my great pleasure to have this opportunity to present our team's research achievements in past few years. So today, my title of my talk is Tensor Representation for Machine Learning. In particular, we focus on efficiency and reliability. So my name is Qibin Zhao. I'm leading Tensor Learning team at RIKEN AIP. Okay, as we know now, the main trend of AI field is large language model, and the large model also we call it foundation model something. And the scaling laws give us some clue that the model can be grow very large, and we need, if we have sufficient data samples and the data set and a sufficient computational resource, we can get emergent of intelligence. And here is some statistic about GPT. Like now, even the model size is become even more than trillion number of parameters. Okay, first we will talk about data efficiency. So how we can learn from small number of data samples using more information from data. So we start from a simple studies. It's a simple linear latent factor models. So we have data Y, and we assume that there's a latent factors eta with a linear transformation W. And we try to find, in general, we can compute the covariance matrix W as a low-rank approximation to the covariance matrix V. And if we use tensorization technology, we tensorize the data Y, and the covariance matrix become covariance tensors, which is a high order. Then we can apply tensor network to approximate these covariance tensors. The results show that if we consider such intrinsic structure and the parameter structure, and we can reduce the data samples to get a better accurate estimation of covariance matrix. So now the question is how we can use data structure or parameter structures. Then we study a lot of work from this basic fundamental problem. So we have a tensor data, and we try to capture the data structure using the few entries. So this is about tensor completion problem. If we use only few entries to capture the whole structure, high dimensional. And we care about the data efficiency and the scalable and the efficient algorithm. Also, we want to have theoretical recovery guarantee. And the most popularly, we assume the low-rank approximation. So we try to impose low-rank needs or nuclear norm optimizations or low-rank tensor decomposition model to try to capture the data structure. So this is a simple examples. Even the data is not originally high-order tensor. So we can use tensorization to change the data from low-dimensional, like a two-dimensional matrix, to high-order tensors. Then tensor network can be applied to get more rich structure information, and we have a better reconstruct performance. So this is a simple case of tensor network. We call this tensor ring because we decompose a n-order tensor as n small core tensors, and they connected sequentially as a ring structure. The connection means a contraction between tensors, and the number between the two cores is the rank of tensor network. So now there are many limitations of current tensor decomposition and the tensor network. For example, we need to predefine the distribution of data, which is the likelihood distributions, and also the prior distribution about latent cores. And the structure assumption is about which decomposition structure you will apply, like CP, Tucker, tensor ring, or tensor chain. There are many different tensor networks. So usually it's predefined. And also the current tensor decomposition are mostly multilinear operations. There is no nonlinearity. And in reality, many data is actually multimodal distribution, not only a simple Gaussian distribution or something else. And the data relations between data and the latent factor are nonlinear. And also sometimes the data is continuous time series. It's not just a discrete like index. It's some kind of function on T. So next, we try to improve the current tensor decomposition and tensor network. So first step, we extend the tensor decomposition to nonlinear case. So simply, we can apply the Gaussian process. we will assume each element actually is generated by several latent factors and by using CP structure. After that, there is a nonlinear function. And we give the pre-distribution on this function as a Gaussian process. But the Gaussian process has a limitation, which is the computational complexity is very high. Also, we want to consider not only nonlinear, but robust, like can we consider the correlations between many tensor data, and also efficiency. When we decompose a new tensor, can we decompose it more efficiently, not using standard method? So then we further extended like tensor ring decomposition to this nonlinear tensor ring decomposition. The idea is we decompose tensor Y as many core tensors, and each core tensor is a generative model, and generated by a latent factor Z, and this generative model is F. So then we can use neural network for any such kind of generations. So from this figure, we can use like autoencoder type of structure. So any tensors can using the encoder to get the latent factor Z, then nonlinear mapping to the core tensors, then generated the new tensor. And the second point about the structure, because tensor network, there are many hyperparameters. Like the number here is 3, 4, 5 is some kind of rank. So which rank is optimal? And the topology, we have a ring structure, tensor train, or a tree structure, or even some unknown topology. So which one is optimal for our task? And the permutation, so even there are four core tensors, X, Y, Z, T, but the order is also a matter, because if we change the order, the result is totally different. So question is, what's optimal tensor network structure? And this is a general framework to find the optimal structure. We usually consider model expressivity, which is for example, your task is classification. This is maybe classification loss. And the most important is first term. We try to find the minimal model complexity. So that's, the idea is to use few number of parameters to achieve this task. Then we have developed many algorithms to solve this problem, and we published in last few years. So generally, they always, because this is a discrete optimization problem, so we usually, the main step is sampling. We sample some tensor structure, then we evaluated the loss function based on our framework. Then we try to find the next optimal one. Then we search a few tensor network structure in a fixed area to find the next one. This is some kind of sampling strategy. Okay, so next, also we consider distribution must also be flexible. So here we try to extend the distribution to be any distributions. Then we use the undirected probabilistic model for tensor decomposition. So idea is we try to model the joint distribution between data X and the latent factor Z as an exponential family of distribution here. And the energy function in this distribution family is modeled by a neural network. So here. So, but this is an undirected probability model. So we cannot find the explicit mapping from latent to data. So that's why we need a special prediction strategy for sampling the data. Also, we can extend this framework to time series. Here, each point is not only a value, each point is a function which has a value t. So each tensor element is a function ft. Then we just add a t value into this function. Is similar framework we can extend to some other case. Here, we also study how we can use this basic tensor completion framework to real applications. And this is about combinatorial distribution shift, which always happen in machine learning fields. So we use this, like our training data has some distributions, but test data distribution are different with training data. So this problem can be modeled as a tensor completion problem. And the point is tensor completion usually have discrete index. And now we need to extend this discrete index to continuous index. Then the tensor decomposition is become tensor decomposition for functions. Okay, so next part is about model parameter efficiency. And as we know that over parameterization is already proved, is powerful and useful, and can avoid overfitting in deep learning field. But there are many problems about the interpretability. I think many researchers in the morning already mentioned. And also robustness to adversarial attack is another problem. So one task is, can we do the model compression? So to compress the model to be smaller, but keep the performance similar. And the tensor network can perform this task by using tensor network to approximate the weight parameter W. And then the input and the weight transformation can be modeled using the tensor network operation. Also in the multimodal learning, we can use tensor product to enrich our feature interactions, which include linear, bilinear, trilinear, and even high order feature interactions. And we get rich information. But the point is now the dimension become dramatically increased. So we must use tensor network for weight parameters. Then everything performed as usual. Then the number of parameters only increase linearly with the P, but the model capacity increase polynomially. Okay, now I think many researchers are doing like from a foundation model to fine-tune a downstream task. So in this fine-tune task, low rank method is also very important. LoRa is very well known. So they assume the adapted parameters delta is the low rank matrix decomposition. However, if we fine-tune the model by not using LoRa, but using standard fine-tune, we find that the adapted parameters are not always low rank. So there's a gap between the real, the optimal fine-tuned parameters and the LoRa fine-tuned parameters. So question, can we achieve better approximation to full fine-tuned with adaptation of less parameters instead of LoRa? And this is our proposal. We try to borrow some information from pre-trained weight, like W0. And also we use a adapter, and this adapter is similar to LoRa, but here we use a tensor network. And also here, the pre-trained parameter W0, we consider to use a transformation by a T, and the T is also a tensor network. Then we show that the result is better than LoRa. That means we use less parameters, and we can achieve better approximation to full fine-tuned result. And here, the generated image, we can see that the glass is transparent. It's better than other generated image because according to our prompt, we need to generate transparent. Okay, now we also try to understand theoretically how low-rank parameters and adaptation works well. So because when sometimes we have a lack of data and we try to use the data set for other tasks to learn a model, then we try to transfer this task to a new task which lack of data. And we use this, basically we use this tensor framework to do this. We have many tensor regression data set and models which try to transfer to another tensor regression task. And we give some theoretical results, like we show that if we use low rank transfer, the adaptation is low rank tensors, and we can reduce the error bound. And we can also use some more information from other tasks. Okay, so the third part is about the reliability of deep learning. So I think most people know these examples, especially in some real applications. Maybe it will generate a serious problem when the self-driving car gives the wrong classification result. This is the adversary attack. So currently there are two types of defense. One is the adversary training, which is try to retrain a new classifier using the adversary examples and to change this classifier to be more robust. And the second technique is adversary purification. So this concept is we keep the classifier fixed, doesn't change. We just add a new model, which is the purifier model. And this model, the function is to guarantee any examples past these models, output is clean examples and no any harmful perturbations. Okay, I think both techniques have advantage and disadvantage. And especially adversary training can get better robustness, and adversary purification can have better generalization to unseen attack. So how about we combine them together? Can we get more advantage and less disadvantage? But the answer is no. Even if we adversary training for classifier and adversary purification in front of classifier, we still have some limitation like high training cost and the drop of clean accuracy. And we need a pre-trained generative model to do purification. So we start from adversary purification, how to improve it. And the state art is using diffusion model to do this task, already achieved very successful. But one big disadvantage is when we use diffusion models, and when we add more and more Gaussian noise, sometimes semantic information will lose, and the generated image can be totally changed from the cat to a dog. If we use less Gaussian noise, and it will generate another problem. The perturbation cannot be removed completely. So how to preserve semantic information and improve robustness performance? And this is a question we want to address. And we developed several techniques. One is using guidance for diffusion, because using guidance, we can avoid retraining the diffusion model. We just give the guidance for the inference procedure in the diffusion model, and this is the guidance. And in this guidance, we consider contrastive guidance. That means we compare the positive samples and the negative samples. So positive samples means each time step, neighbor time step are positive. That means we try to not change semantic information much. And the negative pair is different samples. We try to make different samples have better, larger distance. By using this guidance, we can guide the diffusion model to do the purification task better. And another guidance is we can use the classification result as guidance, not just give a diffusion model. And we can train a small neural network, which is relatively robust, but not completely robust. And we use this additional neural network result as a guidance for diffusion. Then we can also improve the adversary purification task. So here we try to, because diffusion model usually pre-trained not for this task specifically. So how about fine-tune this diffusion model to be more suitable for this task? So we can consider the adversary training ideas, but not to train the classifier. We use adversary training loss to guide the diffusion model to do fine-tuning. So then we can show that we can improve the AP with have better robustness performance, and also better generalization to unseen attack. Okay, so how about the tensor network? Tensor network actually have several key features. It's model-free because we don't need to train a model. And it's no training procedure for tensor network. But it's only consider Gaussian noise. So if we apply tensor network to this task, like we try to reconstruct the image and to remove noise, we find that simply apply it doesn't work because the perturbation is Gaussian, not Gaussian distribution. We cannot remove by tensor network, just simply apply. So now we found another phenomena. If we downsampling the image from a high resolution to low resolution, we find the perturbation distribution are changing dramatically from the non-Gaussian distribution to gradually tend to be a Gaussian-like distribution. So that means when we do this tensor network, we need to a different loss function on different resolution. And we define this adversary loss to try to remove these perturbations. And here there are two key ideas. One is we use delta to keep some distance between reconstructed image to the original image, because we don't want to reconstruct too close to original image, because this will include perturbation. And second, we want our purified image, after downsampling, they are equal to similar to downsampled original image. So by using this, it's very effective. And then next, we try to use tensor network to decompose the image on different level of resolution. Then we use this cost-to-fan tensor network representation. So each core tensor corresponding to different resolution. Then in the low resolution, we can use standard L2 norm for Gaussian noise. But when we increase the resolution, we need to use another loss function for adversarial loss function for this task, as shown here. So finally, this is a video to show one example. The bottom is purified image, and the upper is the adversary examples. Maybe human cannot recognize them, but actually this perturbation already removed by this tensor network. So let's review the past research on this field. At the beginning, researchers consider the clean accuracy, robust accuracy, and later people care about if the model can be generalized to unseen attack. And even now, we consider if the model can generalize to unseen data set, because the diffusion model trained on one data set cannot transfer another data set. And also, we care about the training cost and the inference cost. So our model using tensor method, we have already shown that we can achieve better robustness and also generalize to unseen attack and even to unseen data set, because we don't have any model to train on specific data set. We can just apply to any new data set. Training cost is 0. It's very much better than other technique. Only limitation is the inference, because every new samples come, we need to do the tensor decomposition from beginning. This is the one limitation. Okay, besides the supervised adversary problem, we also consider in the unsupervised learning, especially this multi-view learning, which is considered as a robust model, because when you attack any view, you cannot attack multi-view representation. So our question is if this model are robust enough and if it cannot be attacked. And we studied to develop some technique to find that multi-view learning, we can also attack these models. But the loss function is different with supervised learning because we don't have labels. We try to find the perturbation data, and we try to find the distance between the original representation Z with after attack representations. How much difference between this? And after that, we show that multi-view learning can also be attacked. Then we develop a similar technique for the adversarial training for multi-view learning. And we use a contrastive loss and plus the clustering assignment. Okay, this is the result. If originally we don't use any robust technique, after attack, the clustering will become this, so totally failed. And if we use our adversarial training technique for multi-view learning, even the data are attacked, model can be still robust to do the better clustering. Also, we want to understand if the parameters are low rank, how theoretically it affects the robustness of neural network model. And we consider a very simple case, which is tensorized neural network. The weight is a tensor, and the input output is also tensor. So here we call this T-product layer. And we study theoretically how low rankedness affect the performance, especially adversary generalization error. And it shows that error bounds are different. If we use low rankedness, the error bound is much smaller than without a low rank. Okay, yeah. Okay, now in the generative model and the large language models, the reliability are also changed from the simple classification to something. It's called a jailbreak. So if you use a general like a prompt, you cannot get a result. But people can find some special technique to design the prompt. They can get the expected, the bad result. So how to learn this prompt is high dimensional and a discrete space. So we use a tensor method, like the tensor order is the number of tokens, and the size of each dimension is the size of a vocabulary candidate. So this is a huge space for searching a prompt. And we can use tensor method to solve this more efficiently. So finally, oh, okay, I think this is the last page. So finally, in this year, or from last year, RIKEN has established a new project, which called RIKEN Quantum. I think from I presented also data efficiency, model efficiency, but next I consider maybe quantum computing and quantum machine learning is also useful for computational efficiency. And we are starting this project. We also call for postdoc researchers. So in summary, so data efficiency, parameter efficiency, and reliability machine learning are essential and crucial issues. And tensor network already showed to useful to solve representation of high order data, high order model parameters, and even functions. Trustworthy, in particular, the interpretability and reliability will be studied further in our team. And the quantum machine learning we also investigate in the future. So finally, I would like to thank all my team members. They are all excellent. Previously, I presented many work in top conference done by all of them together. Okay, thank you.
Okay, thanks for Professor Zhao's talk. Anyone has any questions? Okay.
Yeah, thanks for the great talk. And I'm wondering, is there any possible to use the tensor network to empower like the large language model, or to borrow the idea from the large language model to create like a large tensor network? Yeah.
Yeah, I think possible. For example, model compression. I think Professor Danilo already done using tensor method to do model compression for ChatGPT 2 or something. And in the last work, we use tensor method, not tensor method to do the efficient search for prompt prompt searching, which is also related to larger language model. Yeah, I think in the future there are many different points or different directions we can study. Yeah.
Anyone has any questions? Okay, it also has, now time is limited. Maybe if anyone has more questions, please discuss with Professor Zhao.
I'm very pleased to meet you here again. Actually, I spent 5 years at RIKEN. During that time, I have the chance to meet many of you here. Those memories remain pretty special for me. Okay, as the title suggests, I will focus on a very small question. Why does CNN, convolutional neural network, work so well? This paper is published in Journal of Machine Learning Research in 2022. At the beginning, we don't have a word toward, but when the AE said our claim maybe a little exaggerated, so I added a word toward. Today, I say this word very frequently. Anyway, this work is collaborated with Tonghui Li, my PhD student. During that time, he was a master student, and with Liqing here and Professor Qibin. This talk consists of 5 parts, starting with the introduction. Well, transformer-based models have achieved great success. However, convolutional neural networks still indispensable. For example, for data scarce applications, resource-limited deployment. Also, it can be served as a feature extractor in hybrid model design. Also, this morning, Professor Danilo also talked about the energy consumption. Because generally speaking, transformer-based models is very big, but for CNN, we can design much smaller, efficient models for some edge devices. But we want to know why convolutional neural networks work so well. The fundamental understanding has lagged far behind. This is mainly because that convolutional neural networks often have a very complex structure. For example, it including convolution, pooling, activation, normalization, fully connected layers. Their complex interaction made it extremely difficult to analyze the behavior of CNN. So in this paper, here we plan to use a unified and simple structure that can approximate the behavior of CNN with a problem tractable. Some researchers have done some pioneering work using a surrogate model to analyze CNN based on the universal approximation theory. Any variable continuous function can be approximated by weight-2 neural network. This is because from a functional perspective, any neural network can be weighed as a mapping from input to output, or mapping of input to output. This looks good. This looks great, but the problem is if we use such a shallow network, the wide service network have to go toward infinity, which is not so practical. So how about increase the depth instead of width, which align with the philosophy of deep learning? We know a function can also be approximated by Taylor expansion. How can we approximate a neural network in a similar manner and keep the convolution operation? Our answer is the Volterra series. Well, the Taylor series is used to approximation a response system that strictly depends on the input at a current time. In the Volterra series, the output of the system depends on the input of all time lags. This provides the ability to capture the memory. And the featured approximation theory says that a time-invariant function relation can be approximated uniformly and up to an arbitrary degree of precision by a sufficiently high finite order Volterra series. This places the theoretical foundation for our analysis. Okay, this is the standard convolution. Use the polynomial-like notation, we can define high-order convolutions. The major difference is that we include the product of input at the different time lags in this convolution. So here we need to distinguish between one-dimensional order 2 convolution and two-dimensional order 1 convolution. The former include the nonlinear terms because it contains the product of input signals, and the later one, the right one is order 1. Actually, it's essentially linear, but it's frequently used in CNN, building block. This is straightforward to extend this idea to order n convolution. Here, look, left side of the equation, x is we don't use the matrix because due to the convolution operation, x1, x2, xn can have different sides. So we just use x to denote a list. It's not a vector or matrix. So. Okay, this notation is kind of straightforward, and all these high-order convolutions are called Volterra convolutions, and we can add them up and obtain such a formula. Looks very like looks like the Taylor expansion, but the only difference is the product is replaced with this convolution operator. Because in deep CNNs, the input or hidden layers are the output of previous layers. So we define outer convolution operator for the analysis of cascaded system. This properties shows that if the input are over the Volterra form, and it will generate a new system where the input is the original input, but we will have a new kernel. This kernel are computed from using the outer convolution. Here, this figure simply shows that the outer convolution will generate kernels with different patterns. This is our main result. Both convolutional neural networks can be represented in the form of Volterra convolution. In this case, we don't need to care about the network's specific structure or its steps. We just uniformly to convert this network into such an equation. To prove this our claim, we just need to show some. First, we show some building blocks can be converted into such a form, and then use the cascaded system. We can obtain our final results. We show that convolution activation, convolution structure can be converted to the form of Volterra convolutions. Actually, it's quite simple. We just use we need to use the Taylor expansion. We don't use the just we can see from the formula. This proof also shows that if we can convert the activation function to a smooth function, all this can be done uniformly. Similarly, okay, here we show that how the left side is shows the output of the neural network to layers. This structure, and the right hand side shows that the result we computed from this Volterra series. They are almost identical, which shows that this conversion is reliable. Here we also visualize the order order 1, order 2, order 3 Volterra series, the result generated by different order convolutions. Just an example, no deep meaning. For ReLU activation, we know ReLU is not smooth at the 0 point, but it can be approximated by a smooth function. So this means this conversion is possible, and we also show that normalization, inception, average pooling, residual connection, they also correspond to a smooth function. And if we follow the routine we show previously, we can convert any building block into the Volterra series. And then if we consider a deep system, we need to stack this structure together. Here shows that the order 2, order 3 structures can be converted to order 4 Volterra convolution. We also give an example. Here means the left hand side is calculated from the cascaded system, and from right hand side it is a standard Volterra series, and both and they give almost identical results. This is the general case about the order N, order M structure. Anyway, it will generate a standard Volterra series, but with new kernels computed from the subsystem. We built a perturbation upper bound, which shows that how the perturbation in the input affects the final result. So far, we can calculate the kernels from a given neural network. We call this manner white box model because both the network structure and the parameters are accessible for us. But what if the black box model, which means that both the structure and the parameters of the network is completely unknown to us? This is actually quite simple. We just generate input-output pairs using the given network, and use these pairs to fit this Volterra series. By solving this optimization problem, we will infer the killer. This means if we have no any knowledge about this network, we can hack this network. Here we also give a simple example. First of all, we can calculate the kernels from a given expression, and then we by solving the optimization problem, we can infer the kernels, and both systems can yield very similar results. What can we do to the kernels? Here we just show a very simple toy example. We trained a 6-layer flow, 5 layers network to perform digital recognition, and then we solve an optimization model to find the optimal perturbation to attack this system. Our purpose is to we hope to add this perturbation to this figure, which is almost invisible. But the final result, after this attack, the final output will completely different from the output of the original network. In this figure, in each figure, the left hand side is the original figure, and the right hand figure is the figure that we have added the perturbation. It's almost invisible. But after this attack, where the data P shows the result, after this attack, the system will yeah the result completely different the original result. Of course, this is just a very simple it's just a toy example. So to summarize, we propose a unified simple and unified surrogate model to analyze the CNN, which captures the memory, nonlinearity, and convolution, and works for white box and the black box. Everything looks great, but unfortunately, we know that the core tensor will expand exponentially. Order 1, order 2, order 3 is naturally due to our research topic tensors. So Professor Qibin has talked about this much. So and these fundamental problems are well known to us. So I just ignore them, skip this. Anyway, if I assume that the core tensor has some for example, have no rank structure, we can significantly compress the kernel, which can mitigate this cursor dimensionality issue. This is my group at in Guangdong University of Technology, and relatively a bigger group, and currently at RIKEN AIP. Of course, Tianyi is also here, but our recent publications, and that's all. Thank you.
Okay, thanks for Professor Zhou's talk. Anyone has any questions?
Thank you for the great talk. One of the advantages of the classical multi-layer convolutional network is that they are very simple to train. You can use a back propagation layer by layer.
Yes.
I wonder how simple or complicated is to train this convolutional Volterra architecture. Maybe it's difficult, or I don't know. I have no idea.
Okay, a very good question. I think the main purpose for developing such a method is not for training a really neural network. We just we hope to understand how the original neural networks work. If we just design such a unified, I mean, this standard form, I think the computational cost is very high. Okay. It's not for practical use, but if we want to attack this system, and we have an idea about the specific structure or parameters, we have a way to analyze this network, maybe like this.
Okay, thank you.
Not for practical use, I guess.
Thank you.
Okay, so for increased complexity of the neural network, in your case, is increase the order of this Volterra. So how you balance the neural network structure and the order? Do you have any good method to choose which order is the best for the approximation? Okay.
Thank you, Professor Zhang. Also, we also discussed this problem when we prepare this paper. Actually, it's difficult, but if we have the neural network at hand, we can use we can use input to generate the output, and then we use this data to fix to fit our proposed model. In this case, if the error is acceptable, we can truncate the other terms. Of course, we want the order as small as possible, but if we want to higher accuracy, maybe we have to increase the order of kernels. But the how to say the good point, good message is that from here, actually we can find that in many cases the kernel should be sparse. Okay, thank you. Yeah.
Thank you very much, Zhou. So it's very interesting that you started from the universal function approximation theory and the work by Chibenko, Sabenko, and Hornik and such like. Yeah, very interesting. And obviously, Volterra series is basically Taylor series expansion with memory. All you have there is memory. So, and the key question you asked is whether your network should be wider or deeper.
Yes.
So what is the answer? If we have a problem, should we go with a few layer wide or many layer narrow?
Okay, very important question. Even this morning, I also think about this question because I criticized that the shallow network have very wide, the widest should go to infinity. In our case, we also need to increase the depth. So seems there are no big difference. But if we, how to say, I just try to temporarily answer this question. For deeper network, we can increase the layers step by step. But for very wide neural network, if we increase the widest, I guess many parameters will be, how to say, affected there. Because we should generate, we should build the connection between older nodes to new nodes. But here, for deep systems, we just add new layers at the end. So I think there's a little different. Also, for for shallow network, they require the widest go to infinity. But here we also show that the kernels often are over very sparse structure. This means maybe we can save the memory. This means that the kernel not so big as we imagine. And if we can apply our tensor decomposition methods, we can get a very compact representation, I guess. Thank you.
Yeah, very nice talk. I wonder, since the convolutional neural network has multi-channels, so can your framework account for multiple channels?
Multiple channels means
yeah, your multiple channel in the same layer. Yeah, it's not.
Okay, in our case,
layers.
In our case, how to say, if we just consider that, or we just regard this neural network is an input, is a mapping of input to output, no matter what's the structure or how many layers, it depends on the input and the output. If this is how to say, activation function are also smooth, so we think it's a smooth function. So we just can use this approximation. I don't know whether I have answered the question because I'm not so sure about the multi-channel problem.
Yeah, because CNN is always multiple channel.
The core, I think, is here.
Each kernel is one channel, so there's many kernel for each layer.
There's no problem. I mean, I think here you can explain this problem. If we start from input to output, all this can be approximated into this form, no matter how many channels in the middle layers.
Okay. The second question is whether your viewpoint inspire new CNN structures.
Okay, so thank you for this insightful question. I think we didn't go that much, especially after this student finished this work. I also want him to analyze the kernel structure or something more, but we just stop there. But your question is very interesting. Since we use this tool to analyze CNN, we should I think it should give some insights on develop new architectures or something.
Okay, thank you.
If no more questions, let's go on the next section.